Well, earlier we mentioned the mean, and as a measure of central tendency. Where's the center of the distribution? Now, population means and sample means, they have different symbols, but they're both simply arithmetic means, what you're used to as an average. Add them all up and divide by the number of observations. So let's look at an example of a sample mean. Estimate the mean of the distribution of returns on a fund based on its returns over the last 5 years. So there we have it, really good returns for the 5-year period. And how are we going to get the sample mean? Well, we're going to add them all up and divide by 5 and get a sample mean of 29.8. And we'll use this as an estimate of the true mean of the distribution. Now sometimes, instead of that simple average, we'll use a weighted mean. So in our last one, we had 5 observations, 5 years of returns on the fund. So our weights on there, by dividing by 5, it would be the same as to say 0.2 times that first one plus 0.2 times the second one. They were equal weighted. Each one had 1/5 of the weight because there were 5. With a weighted mean, we can differ from that. Now looking at the symbols here, we'll say the weighted mean here is the sum over all i's. So we've got the weight here on return I. Okay. And this means I is 1, I is 2, ... out to I is n, as we've indicated here. And we just need to know those weights. Now those weights sum to 1. Just like our 0.2, 0.2, and 0.2 for our 5 fund returns would sum to 1. So say we've got a portfolio, 50% in a stock index, 40% in a bond index, and 10% in cash. And our returns are 12% on stocks for the year, 7% on that bond index, and 3% on cash. How generous. What's the portfolio return? Well, if we use those weights, that is the percentage of the portfolio that's in each of these 3 assets as our weights, we can calculate the portfolio return. So we put a 50% weight on the return on stocks, a 40% weight on the return on our bond index, and a 10% weight on the 3% return on cash. And that weighted mean tells us that our portfolio return under those assumptions is 9.1%. Now that's just one example of how we'd use a weighted mean, and we'll use it in several instances. But the story is always the same. The weights are most often the percentage of portfolio value. Now another measure of central tendency we have is the median. And it's the midpoint of a data set in the sense that half the observations are above the median and half are below the median. Now if we've got an odd number of observations, and here we've got a pretty small data set, it's only got 5 data points in it. But because it's an odd number of observations, we can easily find the mean. We put them in numerical order, from the lowest to the highest. And then we find that middle point. Well, that middle point is 23. So that's the median for that data set. Now, if we have an even number of observations, we're going to find the middle, right? And that's going to be between 2 observations, equal numbers on each side. Here, with them in numerical order, that's between 23 and 25. So we just have to find the midpoint of that. We want to put our median right between those 2 center ones with 3 on each side. And so for this here, it's 24 is the midpoint between 23 and 25. And why do we use the median? Well, it's less affected by extreme values than the mean. If, as an example, consider a mean, or a median rather, for numbers 2, 3, 10, and 21. Well, our median's going to be right there. Now the mean of these, if I added them up, what have we got? 2 plus 3 is 5, and 10 makes 15, and 21 makes 36. Okay? So our mean is 9. And our median is midpoint between 3 and 10. Now look what happens if I change this observation from 21 to 21 million. What's the median? It's still the midpoint between 3 and 10. Hasn't moved at all. What's happened to the mean? Well, I don't know, but it's really, really big now, the average of those four numbers. And so you can see that outlier, an extreme value, can affect the mean a lot, but not affect the median too much. And that's why you see when they use a home price index, they use the median. They don't want, during a period, they don't want a single sale of a very high-priced house to make that statistic bounce around. So rather than using the mean to reflect those trends in home prices, they use the median. The mode is just the most frequently occurring value in a data set. So when we put our ordered observations there, we see there's 2 28s and one of everything else. So the mode is 28. Now, unlike the mean and the median, there can be more than one mode for the same data set. It could be bimodal, 2 modes, trimodal, whatever. But we just have to look at the frequency of occurrence of each outcome. Now, rather than the arithmetic mean, sometimes when we're using compounding, we want to use the geometric mean. So it's used to calculate periodic compound growth rates. Now, if returns are constant over time, the geometric mean and the arithmetic mean are going to be equal. But if there's some variability in returns, which there usually is, then the geometric mean is going to be less than the arithmetic mean. And our periodic return, our formula here, is we take 1 plus each return, we multiply them all together, and then take it to the power 1 over n, the number of observations that we have. So it's really the equivalent of dividing by 10 with our simple average, our arithmetic mean, except we compound these returns instead of adding them together and take the nth root rather than dividing by n. So let's look at an example in how we can interpret this. The returns for Acme Corporation in the last 3 years were minus 9.34%, 23.45%, and 8.92%. Calculate the average annual compound rate of return. So what are we really asking? We're asking, what's the single rate of return that if we earn that on a compound basis for 3 years, our results for that 3-year period would be exactly the same as with these returns that we've got for Acme Corporation. So we're going to take 1 plus each of those. You see that's what we have in parentheses there. So this one, 1 minus, because we're adding a minus 9.34%. The others, 1 plus the percent return. So we multiply all those together, and then because there's 3 of them, we take the cube root. And that gives us 1 plus that, so we're going to have to do our usual minus 1 there, okay, if we ever get to it. Yeah. So we got this, then we subtract off 1 to get our compound growth rate of 6.825%. So if we earned that 6.825% on an investment compounded annually for 3 years, we'd have the same results as if we had put money in and gotten these returns over that 3-year period. Now, our next mean, and possibly our last, is the harmonic mean. And the only use I know of, I'm sure there are some in science, etc., but the only use I know of in finance is to find the average cost per share of stock purchased over time if you invest the same amount each period. So what's changing? Well, the share price changes, so the number of shares that you can buy each period changes. Now, where does this all come from and why do we care? Well, not much is probably the answer, but mutual fund salesmen historically have been able to show people that, look, if you invest $200 a month in this fund, on the months when the fund's price is down, you'll get more shares. And on the months when the fund's price is up, you'll get less shares. And so overall, your average price per share is going to be less than the arithmetic mean. Well, we're not going to worry too much about the importance of the fact that the harmonic mean is less than the simple mean, the arithmetic mean, but there is an LOS here that says calculate the harmonic mean and interpret it. So let's get to the calculation part. Look at this formula right here. At least let me explain to you briefly what this is. N is the number of, let's say, monthly purchases. Okay? And this is the price each month. And so this is the sum of 1 over the price each month of our periodic buying period. So let's say a client invests $1,000 in shares of a mutual fund at the beginning of each month for 3 months. And the prices are $8, $9, and $10 per share. What is the client's average cost per share? Well, what I put first here, rather than that formula, is just how we'd calculate it if we didn't know the formula. We'd say, well, how much did we invest? We invested $3,000 over 3 months. How many shares did we get? Well, the first month, we got this many shares, 1,000 divided by 8. The second month, we bought this many shares, and the third month, we bought this many shares. So in the denominator, we've got the total number of shares purchased. And in the numerator, we've got the total amount of dollars we spent. So that's got to give us the average cost per share. Now, through a little algebra magic, since that 1,000 appears in both the numerator and everywhere in the denominator, we can take that out. We can just get rid of that and say, well, that equals this right here. Well, that, in fact, is the formula. An application of it, this is N right here, 3 payments. And this is 1 over the price of the first month, or I guess that's the last month. Yeah, that's the first month. And 1 over the price of the second month, and 1 over price we paid the third month. Well, that fits the formula exactly now. So now, even if you forget the formula, just remember, the harmonic mean is your average cost per share. So you can figure it directly, or if you need the formula, you can kind of back it out of that direct calculation. And so we get a harmonic mean, an average price per share, of $8.92.6. Well, notice the simple average of 8, 9, and 10 is 9, so it's a little bit less than that. And in fact, we can order these types of mean. Remember, the arithmetic is the largest. We said the geometric, as long as there's variation, is going to be less than the arithmetic, and that's what we see here. Taking the cube root of 8 times 9 times 10, we get 8.963. And the harmonic mean of 8, 9, and 10, well, that's what we just did with our example. That was 8.926. So that's the order, and that's worth remembering. Arithmetic, geometric, and harmonic, the larger the variation in the numbers, the greater the differences between these 3 means. Next up for us here is quantiles. or percentiles or deciles. It's all the same concept, and you probably remember percentiles from standardized tests that say, well, you're in the 82nd percentile, and that just basically means you beat 82% of the people that took the test. So it's kind of your relative position. And quantiles is just the general term. A quartile is 25%, so 75% of the data points are less than the third quartile. A decile is just a 10% segment, so if we say 60% of the data points are less than the sixth decile, those are equivalent ways of expressing it, and 50% of the data points are less than the 50th percentile, the 1%. So for data with 17 observations, the 70th percentile is at the observation 17 plus 1 times 70%. So see what we're doing here. This is n. It's n plus 1. So we add 1 to the number of observations that we have. Then we multiply that times the percentile that we want. And we get 12.6 here. But now that's not the value. That's the position. If we put all these in order, we want to find the position 12.6. That's going to be between the 12th and 13th observation when we put them in ascending numerical order. So for ordered observations, this is 6/10 of the way from observation 12 to observation 13. So remember the formula n plus 1 times the percentile as a decimal, 0.7 here, gives you the position. Then we have to look at all the observations in order and find that position. So let's take a look at an example. What's the third quartile of the following distribution of returns? Well, we know the third quartile is the 75th percentile, right? 3 times 25%. And we've put them in order here. We've got 10 observations. And 75% of those are below the third quartile. So what's the location of that 75%? Well, here it is, 10 plus 1, that's our n plus 1, times our percentile, 75th percentile, and we want the observation, we want the value of 8.25. So if I count these, 1, 2, 3, 4, 5, 6, 7, 8, guess I could have counted from the right. So we want a quarter of the way from 18 to 19. And that's going to be our 75th percentile. So there's the 8th and 9th. And we're going to go a quarter of the way from 18 to 19, which is 0.25. So our third quartile is 18.25%, a quarter of the way from the 8th to the 9th, because that's the position we got for it from our n plus 1 times the 75%, or 75 percentile. A couple more terms, easy ones here, the range and mean absolute deviation. The range is just from the biggest to the smallest. It's a distance. How far are they? So what's our range for these values here? Well, our lowest is 12%, and our highest is 30%. How far apart are they? They're 18% apart. So that's the range. It's just another term, another way to say something about a data set. Mean absolute deviation is the average of the absolute values of the deviations from the mean. Why absolute values? Well, we want distances. Think of this mean absolute deviation as a measure of how spread out the data is. Now, if we didn't take the absolute values, if we just took the average of all the deviations from the means with the signs on them, it's just a mathematical certainty we'd come out to 0. That's how we found the mean, right? We took the average. So we take the absolute value. So we're really measuring distance from the mean as a positive number here. So that's why we take the distances from the mean. So 30 minus 22, 12 minus 22. So that's going to turn into it's a minus 10. So that's going to be a distance of 10. So we add up all those distances from the mean, divide by 5, and that's our mean absolute deviation. Now, I can't think of where we use that in the Level 1 curriculum, and we use standard deviation mostly as our range, standard deviation variance as our measures of how spread out a data set is. But say we were forecasting, okay, and we had over a number of periods our forecasts, and we measured those forecasts against the truth, the mean. Well, our average deviation would be a pretty good indication of how well we had done. We couldn't just use the averages, because if we were 20% too high one period and then 20% too low the next period, they'd cancel each other out. And you go, well, it's 0. You're a genius. But in fact, there was no genius going on there. So that's why we might use the mean absolute deviation, the average distance from the mean of a number of observations. Speaking of variance and standard deviation is simply the square root of variance. And we write standard deviation as the Greek letter sigma, lowercase sigma, and variance is sigma squared. And we write the true mean of a distribution as the Greek letter mu there, lowercase, for the mean. And how do we calculate the variance? Well, it's the average of the squared deviations from the mean. Hey, we already found the deviations from the mean. We took the absolute value of them, added them up, divided by n. So this is just a little bit different. Instead of adding up the distances from the mean, we're going to square those and then add them all up and divide by n. And that's the population. So the assumption there is that we have all the values, right? That's the population standard deviation. And that's how we would calculate that. And if we wanted we get the variance. If we want the standard deviation, we take the square root. And notice that that variance is always going to be positive because all those squared terms we're adding up are positive. Now, if we only have a sample, if we don't have all the possible observations, then we can calculate the sample variance and sample standard deviation. And the sample variance is exactly the same, except we divide by n minus 1 to preserve its statistical properties instead of n. So numerator, same thing. Square the deviations from the mean. Our x bar here is the mean. It's the average of the values of the sample. So that's the sample mean. So we're taking the deviations from the sample mean, we're squaring each of them, adding them all up, and dividing by n minus 1. And that's to get the sample variance and the square root of that, the sample standard deviation. Let's take a look at a numerical example here. Annual returns data, we've got 30%, 12, 25, 20, and 23. What are the population and sample standard deviation? Well, say these were the returns over 5 years. I want to touch on when we'd use the population variance and when we'd use the sample variance or standard deviation. If we were going to ask a question about these 5 years of returns and say, well, what's the probability that that one of those chosen at random would be 25? Well, that would be 1 out of 5, or 20%. But if those were the returns for the S&P 500, And we said, what's the probability of next year's return being 25%? Well, there's not a lot we can say about that. We'd have to estimate that somehow because we've just got a sample. And so it really depends on what we're going to use this for. If you're talking about predicting on a particular set, then you can use the population. But if we're trying to estimate or forecast outside of that, and I say, well, here's a sample of 60 years of returns on the S&P 500. What's the expected return on the S&P 500 next year? Well, that's a different story. And now we're talking about the whole distribution based on a sample, and we'd use that sample, standard deviation or variance. So here we've got the population mean, 22%. We take the deviations from 22%, the differences, and we square all of those. And for the population variance, we divide by n, 5. If, in fact, we were using this in an application where it was just a sample, we'd put all that same data in the numerator, and we just divide by 4. And that would give us a variance of 44.5 and a standard deviation equal to the square root of that, 6.67%. And notice that that sample standard deviation is greater than the population standard deviation because we've divided by a smaller number.